Okay, so last time we went through the gravitational force, but the other place we used gravity was in the potential energy, gravitational potential energy. Remember, our old gravitational potential energy was just mgh, and our old force was mg, and if you took the derivative of this with respect to h, you would get the force right here. We can do the same thing rather than derive it. The new gravitational potential energy is going to be given by this right here, minus g m1 m2 over r. It's not r squared, it's r to the 1 power, and it's minus. Why? Because if I take the derivative of this with respect to r, it becomes a plus and a 1 over r squared, which is my force. So this is going to be replacing this right there. Now, first of all, you'll notice that this is always negative because r could never be a negative number. And m and g, this is all positive. So the potential energy due to gravity is always going to be negative. Also, remember when we did this, we could call wherever we wanted h equals 0. And the reason why we could is because that was to the 1 power. Well, this is not to the 1 power, this is to the minus 1 power. You cannot put wherever you want r equal to 0. No, we have to use u is only 0 out at infinity. If you plug in infinity into here, then this goes to 0. So u due to gravity is only going to be 0 at infinity. Any place closer and you have some gravitational. Remember, u due to gravity is also a scalar. It's not like the forces right here. So we don't have to break it into its components or anything like that. Now that we've got the true potential energy defined, we can now talk about freedom right here. You think you're free. You know, there's a piece of paper in Washington that says you're free, but you're really not free. Really, to find out whether you're free, it means that the total energy of the object is greater than or equal to 0. If it's just equal to 0, you're just free. Well, since kinetic energy is always a positive energy, and gravitational is always a negative, if this is greater than that, then you're free. If this is less than that, then you're not free right here. You might think, I'm free here on the earth. No, you're not right here, because if you were free, you can go wherever you want. Well, I think I can go wherever I want. Well, I say go to the moon. Well, you can't go to the moon right here. You don't have enough speed to get to the moon right here. If someone threw you hard enough, you could be free right there. So let's come back to that one I did on the last one where I had just 3 placed point masses at an equilateral triangle right here. And we'll just hold them fixed for right now, right there. And we ask, what is the potential energy of just this one right here? Well, the potential between these two is given by minus g. They have the same mass, m squared over L. And this is the same right here. So this guy notices just he doesn't notice this, he just notices whatever is affecting him. So there is the potential energy of that right here. If I wanted to free him up, I would have to give him at least plus that amount of energy to free him up. Right now, he's not free right there. Now, what if I wanted to free all 3 of them up right here? Well, then all I had to do is figure out what's the total potential of all of them. None of them have kinetic because they were just sitting at rest right here. Well, if you want to know how many potentials there are in this whole thing, replace them all with springs. You know, I'd have how many springs? I'd have 3 springs, so you'd have 3 potential energies. And so the total potential out of all of them would be minus 3 gm squared over L, and I would have to give it plus that amount to free them all up. Now, I couldn't give all that energy to one of them. If I gave this amount to this one, and then one of these gm squared over L to this one, then he'd be free. And if there's no one else around him, he's free right there. So, okay. Now, let's look at something that's orbiting like we did before. We already said whenever you see something orbiting, you set the sum of the forces equal to mv squared over r, and that's what we got for the orbital velocity. That's just what we had before. But let's look at the energy of this. The energy of this, he's got positive kinetic. Kinetic is always positive. Minus, remember the gravitational is negative right there. Well, we can take our V and plug it right into here. And this coming into here is just 1/2 gmm over r squared minus gmm over r. You notice a half of something minus a whole something is just -1/2. We'll notice it just so happens with gravity, whenever you're in a circular orbit, the kinetic energy is always half your potential energy, so the total energy is always going to be negative, and which means you're bound, right? If you're not free, you're bound. The total energy is less than 0. Now, if I wanted to free that guy up right here, all I have to do is give him enough energy so his total energy is 0. So I'd have to give him positive this amount of energy. If I gave him positive this amount of energy, how could I do that? Make him go faster, give him some kinetic, then I could free him up right there. Well, what if we weren't in orbit? What if we just throw something straight up? If we just throw something straight up on the surface of the Earth, you've got kinetic there. I've got gravitational energy. Remember, the only place it's 0 is out at infinity. And then you throw it goes way up to here, and it stops momentarily. So way up there, you just have potential energy right here. So that would be the energy equation between here and here. But we can talk about escape velocity. Escape velocity is what speed do I have to throw it so that his energy is 0, just is equal to 0. That means he makes it all the way at an infinite distance, and his speed would stop at an infinite distance. Well, that would mean way over here on the right side, r would be infinity, so this would be 0. So that means if this minus this equals 0, since your total energy would have to be 0, we can set these two equal to each other. Or there is the escape speed, which is the square root of 2 gm over the radius of the Earth. You notice our orbital speed right here was gm over the radius of the Earth, but you weren't free when you're orbiting. This is what it takes to free it. For getting off the Earth, this is about 25,000 miles an hour. That's how fast they had to go to get to the moon right here. They had to get up to that speed right here. You had to kind of get away from Earth, escape Earth right here. You notice the air in this room is not going this fast. If it was, it would leave the Earth right here. It's going a lot slower than this right here. If gravity was a lot weaker, like the moon, gravity is so weak, the escape velocity is small, it cannot hold on to an atmosphere. You need a lot of gravity to make the escape velocity big enough so that the air doesn't leave right there. Well, what if we have, instead of straight, what if we have an elliptical orbit? It could be like a comet. Comets are in quite elliptical orbits right here. Now, as you're going around, you don't want to use the sum of the forces equals mv squared over r, because that's only for circular orbits. If you see an elliptical orbit or anything non-circular, go to energy right here. We know that the energy at this point, which is both kinetic and potential, should equal the kinetic and the potential at that point right here. It's just going around like this. It actually goes faster here. It whips around right here. Now, for comets, some comets come back, some never come back right here, and we can tell by what the energy is. If your energy is less than 0, you're not free. You're bound. And if you're bound, that means you're coming back right here. And if your energy less than 0, you're in an ellipse. An ellipse, circle's just a special case of an ellipse, but you're going in an ellipse right here. And the time to return is somehow related to this area. See this green area right here. It's proportional. What's the proportionality? Well, if you look at Earth's orbit, whatever Earth's orbit is represents 1 year right there. So that's the area representing 1 year. If the energy is greater than 0, then you don't get an ellipse, you get a hyperbola, which goes off like this. It never comes back right here. Never returns right here. So that's how they can tell if a comet's going to come back and forth, come back again. They just have to calculate what the speed is and what the radius is at one point. Then you know the total energy. And if you know the total energy, you know how long it's going to take to come back right here. But we also have another equation here. If we look at the forces on this comet as it goes around, the force is towards this point P. So there really aren't any torques about point P right here. And if the torques, sum of the torques is 0, we can use angular momentum. So the angular momentum here should be the same as the angular momentum there. Since we're not going in a circle, we can't say I omega, but we can at least say R cross P. Remember, that was a definition of angular momentum, which is R cross mv, which is the magnitude of R times the magnitude of mv times the sine of the angle between them. So over here, this R times mv times the sine of the angle between them, which is R is that way, V is that way, so it's this angle, is equal to this R times that V times the angle between those right there. So in some ways, that's a much easier equation than this, but you have to know what the angle is. But at the furthest spot, they call that apogee and perigee, the angle between them is 90 degrees because R is that way and V is this way. So if you just looked at these 2 points, then it's MVR equals MVR right there. Okay, so if you see something going in an ellipse, I would probably go to this energy equation first right here. Now suppose you wanted to go to Mars. You keep talking about going to Mars here. Here's the sun. Here's Earth's orbit. Earth takes 1 year to go around, so this area right here corresponds to 1 year. Mars, it takes around 2. It's not exactly 2 years, but let's say it takes 2 years to go around, so this area corresponds to 2 years. Since we're going around this way, if you want to go to Mars, you'd think, well, why don't we just go from here to here? Mars, that would be the quickest way. No, you don't want to do it that way. That would require a lot of effort right here. Remember, we're moving this way at 60,000 miles an hour. To go this way, you'd have to have a component this way to balance that one, and then go this way, and then Mars is going to hit you at 50,000 miles an hour. You don't want to do that. To get to Mars in the least amount of effort, or to go from any orbit to another one, you want to take off here, and you want to come all the way out and catch it on the other side. So since we're already going around this way, you want to go that way. You don't want to go opposite right here. And you want to catch it on that side. And since we know that this area right here corresponds to 6 months, because this whole thing was 1 year, this area right here corresponds to about 8 months, right? Because this is 1 year. So it takes about 8 months to get out to Mars right there. Now, when you get to Mars, when you get out there, you better make sure Mars is there. You'd hate to be Mars way over here someplace. So Mars just can't be, you can't just take off to Mars at any time. You have to take it off such that Mars will be there in 8 months. Well, it takes Mars a year to get from here to here, so he's got to have a little bit of a head start, a certain angle theta up in front of you, and then you can take off. If you miss that opportunity, you're going to have to wait until you're in that situation again, which is quite some time. Now, once you get there, you say, well, I don't like it. It's too red here. I want to come home. There's people chasing me and all this stuff. Well, you can't just come back, because when you got there, where's the Earth? The Earth is 8 months past this point. Well, there's 6 months, so 8 months is over here someplace. Now, if you take another 8 months to get back, when you get back to here, Earth won't be there. 8 months from here, it's going to be way over here someplace. So you're going to have to wait. You have to wait until Mars, right here, is in front of you by an angle theta right here. So if you were taking off from here back, you'd want Earth to be back here, that same angle behind you right here, so that when you get back to here, it gets back at the same time. And that takes, you're going to have to wait minimum almost 2 years for that to happen. So the minimum time for to a trip to Mars and back, 8 months, around 2 years, you got to wait till this alignment, and then another 8 months back. So, you know, it's getting close to almost 4 years for a trip. Remember, we went to the moon, it was only like less than a week right here. It's a big difference from going to Mars right there. So, again, when, you can think of this in terms of time as just areas right there. Now, one other thing here, and that is the black hole right here. Black hole is just where gravity, if you squish the sun, or whatever, even the Earth, you just squish it down, gravity gets stronger and stronger. The stronger gravity gets, the larger the escape speed is. Now, we can talk about the surface of the radius of a black hole is when the escape speed hits the speed of light. So if we just set the escape speed equal to the speed of light, then there was the escape speed equal to the speed of light, we can get the radius of a black hole. So just square both sides and bring the r up and bring the c down. Now when we talk about the radius, that doesn't mean there's a solid surface there. That just means that if you get within that radius, then if you had a flashlight pointing straight up, even the light would bend down. That's why they call it a black hole. If we're talking about the Earth, you're probably talking about squeezing the Earth down to about that big, maybe even smaller, maybe about that big. So again, a black hole is just super, super dense, so that the escape velocity of light is at least the speed of light. There might not be any surface. It might squeeze down to zero size. They don't know. They usually call this the event horizon, this radius where the escape velocity is the speed of light. Okay, so this is pretty much all we needed for chapter 12. This is the last of any new material right here. Again, we're not going to worry about chapter 13 right there. Okay, so good luck.